Okay, so here I have a conjugated diene molecule. Instead of putting hydrogens on each one, I put here we have a green. Actually, we can use green. And do I have and then orange. Carbon here, hydrogen, orange. I'm going to rotate about this bond. I'm going to keep this exactly the way it was. But I can rotate about this carbon-carbon single bond. There you go. And now you notice the green and the green and the orange are away from each other. Okay, this is referred to an S-trans conformation. So these two are as far apart as possible. Here, they're as close as possible. This becomes very important later when we talk about the Diels-Alder reaction. So again, S-cis conformation, essentially the two double bonds are kind of pointing in the same direction. You can't rotate about a carbon-carbon double bond. It's stuck because it's fixed in two places, right? But you can rotate about a carbon-carbon single bond. So we have S-cis and now S-trans. The two double bonds are facing away from each other. So those are not resonance structures. Those are not isomers. They're just same compound, just different conformation by rotation around that sigma bond. So if we have, remember there were three different conformation or three different stereoisomers. It could be cis and cis, or Z and Z. We could have trans and trans, so E and E, or we could have cis and trans. So these are cis, both cis. If it's trans, you notice when it's cis, it kind of has puts a kind of a kink in the molecule. When it's trans, it's more or less straight across. Put the hydrogens in. This is a different isomer now. This is cis and cis. This is trans and trans. So two different isomers. This isomer has two different conformations. Right? We could have the S-trans conformation or the S-cis. This is still a trans double bond. Right, so these two are on opposite sides. And these two are on opposite sides. So this is a trans double bond, this is a trans double bond. We just rotated about this carbon-carbon single bond to get this, actually it would be this double bond moves up. All right, a little practice drawing dienes. We had this before in the chapter on alkenes, but we can do a little bit more of this. So what I would recommend first is draw the structure of the compound first, and then put it in the two different conformations. So octadiene, all right, so that's 8 carbons, 1, 2, 3, 4, 5, 6, 7, 8. We have double bond on carbons 2 and 4. 1, 2, we'll put a bond. 3, 4, we put a double bond. Okay, so now we've got the 2,4 octadiene. What we have to do now is make sure that they're both E. So put the hydrogens in. They're on opposite sides, so that's E. So don't get confused, I'll use green here. These are likewise on opposite sides, so this is E. The way I've drawn it now is essentially in the S-trans conformation, but what I want you to do is take this single bond here and put it vertical. Okay, so this is carbons 1, 2, 3, and 4. So carbons 3 and 4, I'll put a little 3 here, and 4. On carbon 3 we have a double bond, and if it's in the S-trans conformation we go off to the left. So that's carbon 2, and then we want to be sure we don't mess up the trans business. So we have a hydrogen coming off this way. I need the hydrogen coming off this way. So the methyl group, which would be carbon 1, right, is here. So 1, 2, 3, 4. It's trans. For carbon 4 now, 1, 2, 3, 4, we have a double bond. It has to go in the opposite direction. So S trans, the two double bonds are facing away from each other. Again, we want to make sure that we maintain the E and E stereoisomer. On carbon 4 we have a hydrogen coming off here. That means we have to have the other hydrogen coming off this way, so they're on opposite sides. And then the rest of the molecules is carbon 4, carbon 5, carbon 6, 7, 8. Carbon 5, 6, 7, 8. Okay. So this is 2,4-octadiene in the S-trans conformation. For the S-cis conformation, we're just going to rotate about this carbon-carbon double bond. So we have this one done. We can just kind of copy it. Put this bond between carbon 3 and 4 vertical, start there. Put a double bond going off to the right. The other double bond going off to the right. Where the methyl group was going to the right, now it's going to be going to the left. And we'll put the hydrogens in to make sure that they're still trans. Where we had, well, this part hasn't changed actually. We just rotated the top. So 5, 6, 7, 8. Hydrogen. Okay, and put the hydrogen. So S-cis conformation, the two double bonds are facing the same way. S-trans conformation, the two double bonds are one's to the left, one's to the right. All right, so we saw this way back. This next idea here came way back in when we first started talking about benzene. It's got these double bond, single bond, double bond, and we know double bonds, right, are shorter than single bonds. So in benzene, it doesn't actually look like this, but the double bonds would be shorter, and then we'd have a longer single bond, and then we'd have a shorter double bond, and we have a longer single bond, and a shorter double bond, and I kind of messed this up a bit, but okay. We know it doesn't look like this. In benzene, all the bonds are the same length, and that's due to this resonance hybrid. We see something similar in these conjugated dienes. The double bond, we have, I'll draw a cis conformation. We're talking about this single bond here. We've got a double bond, single bond. We saw the same sort of thing here. Double bond, single bond, double bond, single bond, double bond. This bond is shorter here, and it's shorter here as well. So whereas a single bond would normally be 153 picometers, here it's a little bit shorter, 148. Not that that makes a big difference, but remember the shorter the bond, the more energy there is. So shorter, I should say stronger. I shouldn't say more energy, but stronger. So they mentioned here. Conjugated dienes are more stable than isolated dienes, and what we mean by that is, if you remember, let's just make an isolated diene like this. We had in chapter 11 all sorts of reactions. We had bromination, we had hydration. This reaction would go fairly quickly with this type of compound, but with an isolated, with a conjugated double bond, single bond, double bond. Right? In the conjugated system here, this will be slower. it's more stable. And that's because double bond character is not as strong in a conjugated system as it is in a isolated system. The reason for that, the double bond here, this electron cloud here, is smeared out over all three of these atoms, where here it's just isolated here and here. So that's what they're referring to as being more stable. You see the same sort of thing with benzene. Remember benzene, you draw it as a calculi structure. If you were to add bromine to this, you get no reaction. You can do this if you add a catalyst like iron bromide, but you do not get the addition reaction. In other words, the double bonds stay, and instead of adding across the double bond as you normally would in an isolated system like this, you substitute a bromine for a hydrogen, so it doesn't undergo addition reactions, it undergoes substitution. Similarly here, you would still get addition here, but it would be slower than if it was isolated. So I was talking about double bond character. In the longer isolated system, 153 picometers, each one is sp3 hybridized, but here they're sp2 hybridized, so the s character is greater. Remember, s orbitals are centered on the nucleus, and if it's sp2, it's 33% s, so it's more centered on the nucleus, which means it's closer to the positive charge of the nucleus, whereas p orbitals, right, are further away from the nucleus. So if it's sp3, the s character drops, and those bonds are not, electrons are not held as tight, so the bond is longer. So here they're just explaining the difference between why this bond is shorter in a conjugated system than in a regular isolated system. Here I was talking, this is a conjugated system, and I was saying how this double bond is kind of smeared out. You see that here there's this partial double bond character in these resonance structures. Okay. So the hybrid, you see the double bond character kind of smeared out among all four atoms. What is the conjugation? Well, there's a single bond here, a single bond here, there's a single bond to this hydrogen, 1, 2, 3 bonds. This is sp2. This is a carbocation. So let me draw a carbanion. It's got a negative charge. Do it this way. So carbon 1, carbon 2, carbon 1, carbon 2. Remember, sp2 means trigonal planar geometry. Okay, so this bond here is a sigma bond. So we have unhybridized p orbital with a pair of electrons in it. It's not bonded to anything, so it's got a negative charge. Remember, carbon, if we have 4 bonds, it's neutral, the charge is neutral. If we have 3 bonds and no lone pairs, carbocation is plus. If we have, I should maybe do it this way again, 3 bonds with a pair of electrons here, it's minus. Carbanion, carbocation. So here we have a conjugated carbanion, and this was one of the resonance systems that we talked about. We have a negative charge next, an allylic charge next to this double bond. We can move this pair of electrons in, move this out, so the negative charge doesn't go to the adjacent carbon, it skips one, hops over here when you have the double bond. In both of these, we have the same number of bonds and charges. Right? So a negative charge, 1 double bond, negative charge, 1 double bond. So given those rules, we would say, okay, they're equal contributors to the resonance hybrid. However, this is a terminal alkyne, and it's alkene, So it's mono-substituted. Here, when we move the double bond here now, it's di-substituted. And we know from way back when di-substituted alkenes are more stable than di-substituted. So in terms of the resonance hybrid, yeah, they're equal contributors to resonance hybrid, but this is a more stable alkene. What is the hybridization of indicated carbons? We've got an unpaired pair of electrons here. Right? This is going to have a negative. I'm going to put the negative charge in, but this is a negative charge. It's going to be sp2. This guy has. This is an oxygen with 3 unshared pairs. It's also negative. Okay? It's also negative, but this can be sp3. In a later chapter, we'll see where this can change, but for now, it's sp3. I think that's actually the very next chapter. Okay, again, carbanion, just as we had here, they just included the hydrogens. This would be sp2. The way we can determine the stability of conjugated dienes is through a reaction like this. So if we look at a reaction diagram, I won't put the activation energy in, but we have the alkene, and then it goes to the alkane. The difference in these is the delta H, the heat of hydrogenation. Okay. So we could measure, when they talk about the heat of hydrogenation or the stability, if it's isolated, alkene, diene rather, isolated diene, it'll have a higher heat of hydrogenation than if it was conjugated. So I just put here conjugated. So I'm just reminding you here how these are measured. You end up with the same product. So this is 1, 2, 3, 4, 5. So 1, 5 pentadiene, or sorry, 1, 4 pentadiene. We could have 1, 2, 3, 4, 5. We could have the conjugated 1, 3 pentadiene. Their isomers of one another. They'll give you the same product, simply pentane. 1, 2, 3, 4, 5. So they end up in the same place, but this has a lower heat of hydrogenation, so it's more stable. Right, so the isolated diene, heat of hydrogen, they end up in the same place, 1, 2, 3, 4, 5. End up with pentane. The conjugated is more stable. We've already talked about this, how the double bond is spread out among all 3. So you get these partial double bonds, if you wish. And the double bond, the single bond here in the static structure here actually is shorter, has more S character. Okay. Rank these dienes in order of stability. So what we're looking for here is conjugated or isolated. Double bond, single bond, single bond, double bond. So this one is isolated. Double bond, single bond, single bond. So this one is also isolated. Here, double bond. These are all isomers, by the way, right? So double bond, single bond, single bond. This one is isolated, but this one here is conjugated. This one is isolated. All 4 of these are isolated. Here we have 2 that are conjugated. Here we have these 2 that are conjugated, but this one has moved up, so now we have 3 that are conjugated. This one is isolated. So in stability, it follows A is less than B is less than C, or C is greater than B, B is greater than A. Just a brief review of electrophilic addition. You can add across a double bond. Let's add HBr. And this double bond opens up, bonds to this hydrogen. Oops, hydrogen. This is a hydrogen I just added. Double bond is gone. That generates a carbocation here. And it's a secondary carbocation. Notice the hydrogen goes to the carbon with the most hydrogens, generates a more stable secondary carbocation, and then the bromide ion bonds to the carbocation. So Markovnikov's rule, the hydrogen goes to the carbon with the most hydrogens. In this case, the bromine goes to the second carbon, so we get 2 bromopropane instead of 1 bromopropane. So, alright, so that's fine. Now, with conjugated dienes, you're going to get a mixture of products. With isolated dienes, you don't. So an isolated diene, we're just going to add one equivalent, so we're just going to add it across one of these double bonds, not both, and you just get one. Remember, the more stable carbocation, this is a secondary carbon, so we've put the bromine here, not on the end. Okay. With a conjugated diene, you get a mixture of products. You get the 1,2 product and the 1,4. So carbon 1,2, we just added across just as we did before. But you also get this goofy 1,4 product. Notice here the double bond has actually moved. Okay. The reason for this is the resonance of the carbocation intermediate. That generates this 1,4 product. And again, the reason we call it 1,2 is the hydrogens are added, the hydrogen and bromine is added across 1,2, just as normal as if we didn't even have another one here. But in the 1,4 product, we add a hydrogen and carbon 1, and then 2, 3, 4 carbons away, we add the bromine. So carbon 1, carbon 4, we add the bromine. So instead of being right next to each other, they're 1 and 4. So the same reaction we've seen many times before. First step is the addition of the hydrogen, generating the carbocation. This is a slow rate determining step. We generate a secondary carbocation, and it's allylic. And remember the stability of carbocations that I talked about. Secondary allylic carbocation is even more stable than a tertiary carbocation. So this reaction actually goes fairly quickly. This is the slowest of these steps, however. Now we can draw the resonance structure. So here we have the resonance arrow. Move this pair of electrons over. We get the double bond. The carbocation leapfrogs, doesn't go to the adjacent carbon, goes 1,3. Okay, and then it is the bromine, or I should say the bromide, that attacks this carbocation. So in step 2, the bromide could either attack here, we get the 1,2 product, or it could attack here and we get the 1,4 product. Now, if you recall, I mentioned that this is a terminal alkyne. It's monosubstituted, and it's less stable than this internal alkyne, which is disubstituted. So monosubstituted. Right, disubstituted, we have 2 alkyl groups, 2 carbons attached to the carbons in the double bond. So this is disubstituted, more stable. You think, okay, well, does that mean that the 1,4 product is going to be favored versus the 1,2? It depends. Okay? So, even though this is more stable, are there instances where the 1,2 product is favored versus the 1,4? The answer is yes. We'll take a look at that in a little bit. So draw the products of the following reactions. We're just going to add, this is just to remind us how to do these reactions. We're going to add HBr across here, and we'll do the the 1,2 product. Okay, so this was 1,2 addition. Now, Markovnikov's rule doesn't come into play here because there's one hydrogen on each one of these carbons. So we could get this guy, and we also get, I made him too big, but I'll put him down here. We could get this one. Actually, there would be 2 hydrogens here now. So those are both 1,2 products. That double bond stays. Okay, but if we make put that hydrogen here first instead of this one, if we put it here, remember the hydrogen goes here, the carbocation would be here, and it's not allylic anymore, right? But if we put the hydrogen here, this would be the carbocation to which the bromine attacks. So this carbocation is now allylic, so we could also get the 1,4 product and move that pair of electrons over. So we added the hydrogen here, generated carbocation here, which then moved down to here. We're going to put the double bond there. These hydrogens are the same hydrogens we started off with. The bromine attacks here now, and we get the 1,4 product. So there's in fact 2 different 1,2 products and a 1, 2, 3, 4 product. For here, it doesn't really much matter. We'll just add the HBr to these guys. We're not going to mess with this one. HBr, it'd be the 1,2 product. These are not conjugated, right? Double bond, single, single. This is sp3 hybridized. That's it. That's all you get. This is conjugated double bond, single bond, double bond. So it does matter somewhat to which double bond you add to. I'm going to add to this one primarily because this is going to give us a tertiary allylic carbocation. So if, let me draw the mechanism here. If I put the hydrogen here, right, pair of electrons goes like that, bonds to this hydrogen, this pair of electrons goes on into the bromine. There's a hydrogen here as well. I'm going to stick that hydrogen here. That makes this a carbocation, and it's allylic to this one. Okay? So the 1,2 product in the second step, adding the bromide, okay, I added the hydrogen here, generated a carbocation here. Bromide bonds to that carbocation. We leave that double bond alone. Okay? But we also have resonance where we can move this double bond in like that. Oops, sorry, there's no hydrogen there. This is a methyl. So if we do the resonance structure here, we'll put the double bond here. There's a hydrogen here as well. This becomes the carbocation to which the bromide attacks, and we get the 1,4 product. Okay, so we added the hydrogen here, generated a carbocation, did the resonance structure, so that's the same. Double bonds moved over, and now we have the bromine here, and we have the 1, 2, 3, 4 product. So the 1,4 product, the 1,2 product.